All right, screen is shared, recording is started. As usual, I'll hang around after class if people have questions. I know you're working on project 4 right now, and like I've said in a couple of the announcements, that tends to be the one that people end up putting in the most time on. We try to make them a little bit easier after this. You'll be doing more stuff, but you'll be better at some of the fundamentals by then, so hopefully that'll make for easier projects. Today, we're going to be continuing what we talked about last time, using some features of the C language that make it easy to get at the underlying bitwise representation of various types. Java has mechanisms for doing this as well. It's just, I know most people coming through our curriculum haven't seen that. I mean, this is the class where we kind of talk about that first, or at least where we decided to in the design of the curriculum. And it's more typical for what you would do in a language like C. Often you're working closer to the hardware. So it's nice to have operations that let you look at the individual bits inside a value. So to work with the bits in a number, we're going to have to review, or we're going to have to learn 6 new operators. They're almost identical between C and Java. There's a little bit of a difference, or one particular place where there's a difference. And then using those operators, we'll figure out how to do some standard tricks that you might do if you had to look at the bit representation inside an int or inside any other type. And kind of the final thing we'll figure out how to do this is to take, or what we'll figure out how to do with this is to take a number like a 32-bit int and kind of carve it up into individual bit fields and use those fields to store smaller values, maybe ones that don't require a whole int. Now, why would you need to do this? Why would you care about, like if you had a number like 75 stored in a variable, why would you need to access the individual bits that make up the representation of that number? Normally, when we have an int, we just want to use it as an integer value. We want to use it to store a number, well, typically in the range from about 2 billion, negative 2 billion to positive 2 billion. I can come up with some reasons why you might want to look at the bitwise representation, and I listed them here. One of them might be if memory is really scarce or you're storing something really big, you might have to get creative in how you store it. You might have to pack more than one value into each byte. Some basic operations pertaining to compression and encryption also depend on looking at numbers or encoding things by working with individual bits. Kind of the same idea to give us access to kind of a lowest level representation. If you're writing code that works with hardware, like that programs a graphics card or builds network packets to send out over the network, those are often specified down to the bit level, so you've got to be able to write code that works with that. And some processors can give you very low-level parallelism. They can effectively do a lot of operations at once by doing one thing with these bits and then doing something else or a different operation with the bits right next to them. Now, the standard library, at least until more recent versions of C, in C99, there was no standard way of working with bits, or at least of specifying numbers in binary. That's why we bothered to learn things like octal and hexadecimal. And even though newer standards of the language do let you work directly with binary numbers, and what I mean is like I'm showing here on the slides. In C99, you couldn't say, oh, I want I to have this sequence of bits in it, or I want to read from the user a number that they're going to type in as ones and zeros, or I want to print out a number as ones and zeros. Newer versions of the language give you a little bit more on that, but people still use octal and hexadecimal most of the time when they're trying to work with binary, when they're trying to work with the bits in a value. And the reason is because it's a lot shorter. Like we talked about last time, in hexadecimal, every digit represents 8 bits. In octal, every digit represents 3 bits. And if you want to write down a number where you get to choose the bit pattern in that number, those other 2 representations, octal and hexadecimal, are a lot shorter of a way to do that. So if we want to work with the bits that make up the values that we normally use inside an int or any other type. I mentioned we're going to need 6 new operators, and we'll spend some time on each of them individually. But I've listed them all here, and I included them in the same precedence table we've looked at before. So this shows how they fit in precedence. I colored the new ones in red. So there's a bitwise complement operator that's written as a tilde. It's a unary prefix operator. So it just has one operand and it comes before its operand. And informally, it flips all the bits. That's like the name suggests, bitwise complement. You give it a value that's made up a bunch of bits, and it gives you back a value that's just like that one, except all the bits are flipped. All the zeros become ones, all the ones become zeros. That one has pretty high precedence. It's in that second to highest precedence category. The next two are almost near the bottom of this table. The bitwise shift operators. These take bits and they move them left or right. We'll talk about that in more detail, but informally, they're good for moving bits around in a value, where around means either left or right. And then the next three are on this part of the table. There's a bitwise and, a bitwise exclusive or, and a bitwise inclusive or. And the thing to notice with these, well, to an extent with the shift operators, but even more so with these, is they have really low precedence. I mention that because it's easy to make mistakes with precedence when you're using these operators. We're so accustomed to things backing up, things like plus or times, and we know how their precedence works. Notice that these are way lower, even lower than the equality tests. So it means if you write an expression and it includes the and operator and an equality test, the equality test actually has higher precedence. Often using these operators, you'll end up putting parentheses just to force them to have the precedence you want, to force the operators to do their job in the order you want. So we'll see some more examples of this, but just keep in mind, especially these three operators we just talked about, they have sometimes inconveniently low precedence.
Is the order there the precedence of those operators?
Yes, so this table split across 2 slides. And I colored them based on their precedence. So this is the highest category. All of these are tied for next highest. And then these are next highest, these are next highest, and then these. And continuing on down to here, each of these has a different precedence, but you're right, they're ordered. So of these 3, and is slightly higher. Caret, bitwise exclusive or is slightly lower than and vertical bar is slightly lower than that. Other questions? All right, one thing that you should, or you kind of have to get used to when you're looking at bitwise numbers is you might see the effect of something called sign extension. And I've got an example here that just shows this happening, and I'm showing you this so that it won't surprise you later and you can understand what you're really seeing when you see this. Normally, when we work with a variable of type char or short, we already know that that gets stretched out to int size whenever we try and do math on it. We learned that when we were looking at the usual arithmetic conversions. The same thing can happen when you try to print out a value. So here I make a couple of chars, X and Y. One is signed and one is unsigned. I put a couple of values in these. I use hex because I want to think about these values as binary. And we learned last time, well, hex A9 would be 1010. I'm not cheating by looking at this over here, but I could. 1010 and then 1001. And then I do the same thing with Y. So they start out with the same bit pattern. But when I print these out, well, even though they're only character size variables, they get stretched out to be integer size when they get passed to printf like this. This X is going to print out, and you remember from last time, this %X says print this thing in hex. So X is going to print out just like you expect. it's going to print out as A9. We said to print it in hex, and we get the same hex value we gave it. No surprise, but Y is going to print out as FFFFFA9. And all those F's are really the result of it being stretched out. And it's because of how negative numbers get extended when you go from a narrower type to a wider type. Here, when we made Y, we said make it a char, make it 1 byte in size. But we said use it to store a signed value. And this A9 is interpreted as a negative number. You'll see that in assembly language class, but for the standard way negative numbers are represented, this 1 here marks that as a negative number. When that negative, and specifically negative 87, if we wanted to look at it in base 10 in decimal, when we stretch that 1 byte negative number out to a 4 byte, a 32-bit negative number, to keep it having the same value, we have to put F's here. Otherwise, it wouldn't look like a negative 87 anymore. It would look like it had a different value. So the short answer for how this is done is all of these extra bits. So these 2 hex digits is all you would need if it was a 1 byte value. But if it's a 4 byte value, if it's 32 bits, all of these extra F's are the extra bits that had to get added, and they're really just a copy of that sign bit. They're a copy of this 1 here. To keep a negative value having the same value so that it doesn't seem to change value just because you stretched it out to 32 bits instead of the 8 bits we started with, you have to do this trick that's called sign extension, copying the high order bit into all those new extra bits you had to add. When you print out a number like we're doing here, you might see the effects of sign extension. And again, if it didn't happen, if this top bit for a signed number didn't get copied into these higher order bits, it wouldn't look like an 87 anymore. The computer would think it had a different value. This doesn't matter for unsigned values. For X, we said, oh, it doesn't need to hold any negative values. So it doesn't have to use sign extension, but signed values like Y, they do have to use that. And again, this is just a heads up because you'll probably see that. All right, I gave you a quick overview of 6 operators that we're going to see. And here's the first one. It was the highest precedence, the bitwise complement operator. It's written like a tilde, and you just put it in front of the thing you want to complement. It's kind of like negation. In fact, its 2 most similar operators are negative if you wanted to negate a numeric value, or not if you wanted to negate a Boolean value, if you wanted to complement it. But this one's different because it flips every bit in a value. Or really a better way to say it would be, it gives you back a value that looks just like its operand, but with all the bits flipped. So here I make 3 variables, X, Y, and Z, and I put in X, I put 1A, and I did that in hexadecimal, so it's easy to read that as 0001, 1010. If you put a complement in front of that, you get all those same bits, but all the zeros turned into ones and all the ones turned into zeros. And I wrote that down here to try and make it easy to see. This high order 0 gets turned into a 1. This high order 0 gets turned into a 1. This 0 gets turned into a 1. This 1 gets turned into a 0. Now, just like these other 2 operators, complement doesn't actually change its operand. So this doesn't change X. It just computes a new value that looks just like X, but with all the bits flipped. It's really just like an arithmetic operation. So when you do this, this 1 byte value X gets, just like we said before, gets stretched out to integer size, which means it gets sign extended like this, or it gets sign extended, and then we flip all the bits. So right after you complement it, it really looks like this picture I've drawn over on the right. It's just when you assign it to Y, Y doesn't have, since Y is just another byte, it's just another character size variable, It doesn't have room to store all 32 of these bits, so it just keeps the low order 8. So if you look at Y after this is done, it'll just have the 8 bits that I'm showing here. Questions before I try to move on?
So if y was of type long, it's gonna store like all of those ones.
Yeah, if you stored it in long or even just a plain old int, you would
Okay.
see the result of the sign extension. So the order that this happens is before x even gets complemented. It sign extends it, or really it stretches it out to be integer sized, and then you flip all the bits. When you take this 1a, and here I said sign extension, I probably shouldn't have said that because these are unsigned variables. They still get stretched out to be 32 bits, integer sized before you do the math. But because they're unsigned, they don't really get sign extension. They just get extra high order zeros. Sign extension only happens for signed values. Other questions, or does anyone, if you want to do over on that last question? All right, before we move to the next slide, I mentioned tilde is kind of like the two other negation operators, but they all compute different things. Tilde flips all the bits. Logical not just switches from true and false. So if you had x like this, well, that's non-zero, so it's true. So not x would evaluate to false. That would be 0. Negation negates a value, and we'd have to understand a little more about 2's complement to make sense of this, but if x was 1a, then negative x is going to look like what I've drawn here, 1, 1, 1, 0, 0, 1, 1, 0. So kind of like what you get with tilde, but not exactly the same value. All right, that's 1 out of 6 operators. We've got 5 more. But we've covered some of the details already. The next 3 we can cover all at once. There is a bitwise and or and inclusive or operation, or really I should say and exclusive or and or. Usually this one at the bottom is just called or, and the one in the middle is called exclusive or to distinguish between them. They work kind of like, I mean, you've already seen operators that look kind of like this. Double ampersand and is good for building logical conditions, gluing together 2 smaller conditionals to a new one that's true only if both of the 2 that you put together are true. Or is the same way, except the result is true only if its 2 operands are true. These are different though, because instead of just computing one truth value, they work across all the bits in their 2 operands at once. They've got names similar to things like the and the or that you've seen. It's just they work individually on each of the bits. And I've got a picture to try to show this. For a lot of these pictures, I'm showing bitwise operations, kind of like how you would write out a math problem if you were in elementary school. You might write down one of the operands, and then below it, one of the other operands, and then the operator you're doing over on the left, and then usually a horizontal line and the result at the bottom. I did the same here because it makes it easy to look at what happens to each individual bit. So if you had 2 bytes and you ANDed them together, instead of just resulting in 1 bit worth of result, it gives you 8 bits of result, 1 for each bit in the 2 operands. So this bit, the lowest order bit in the result, is the AND of the 2 lowest order bits in the operand. So this is 0 because these were both 0. This next bit is 0 because, well, one of these input bits was 0. Just like a conditional AND, just like logical AND, the resulting bit is only true. It's only 1 if both of the inputs are 1. So 0 ANDed with 0 gives you a 0. 0 ANDed with 1 gives you a 0. 1 ANDed with 0 still gives you a 0. You only get a 1 if you have 1 ANDed with 1. And we've covered all the cases. The rest of these are just more copies of the same cases. So bitwise AND does this operation across each of the bits in 2 operands. Bitwise OR, same idea. It does the same kind of computation as the OR operator. It just does it bit by bit. So just like OR, the result is 0 if both of the input bits are 0, but if either of them are 1, the resulting bit is 1. And even if they're both 1, the resulting bit is 1. So that's the, and you know this from previous classes, that's the inclusive part of inclusive OR. Even if both of the input operands, input bits are 1, the output bit is still 1. The one in the middle is exclusive OR. Well, we didn't really have a logical operator for that. We secretly do. We just don't think of it that way. But we do have a bitwise operator that's made for doing that. Exclusive OR is a lot like the inclusive OR. It just differs on this one case. If both of the input bits are 1, then the output bit is 0. So the output bit is 1 only when exactly one of the input bits is 1. Down at the bottom, I've shown the 2 operators that you're already familiar with, logical AND and logical OR. I'll remind you, they really just care about true and false, whether you're in Java or C. So as truth values, well, this top operand, same as the one I had up here, is true because it's non-zero. This bottom one is also true because it's non-zero. So this operator gives you an output that's true because both of the inputs were true. Similar for OR, either of the inputs is true. Well, here they both are, so the output is going to be true. These operators at the bottom are guaranteed to short circuit, and the ones at the top don't. I don't even know if that would make sense for these operators. They don't have any kind of built-in short circuiting behavior, but these 2 that you already knew about do. Questions? We got 2 more operators to try to talk about. All right. We skipped over the ones in the middle of our precedence and we called them left and right shift operators. They look kind of weird. The left shift operator looks like 2 lesser than signs right up next to each other. And what it does, like I've tried to show in the picture, is it takes the bits in the left operand and moves them to the left by however many bits you say in the right operand. So in this example, you're saying, I want the bit pattern for 1A. That's what I drew down here. So it's 0, 0, 0, 1, 1, 0, 1, 0. I want that, but I want you to slide all the bits to the left by 5. So the result is going to look like this. All the bits you started with are 5 positions to the left. And it's always going to put in extra low order zeros to fill in any space. So here in the output, I get 5 low order zeros over on the right. And you can think as these bits get slid to the left, new low order zeros get introduced. This operator makes it easy to slide bits around, not just 1 bit at a time, but you could put any value you wanted here to shift bits by a whole bunch of positions at once. The only shifts that would make sense would be ones that, well, let me try that sentence again. If you shift too far, then you're essentially throwing away one of the operands. If you took this number and said, shift it to the left by 1,000 bits, there'd never be a reason to do that because that's just going to slide all the bits off the high order end. You're always going to get a result of 0 in that case. So the shift should always be between 0 and n-1 for an n-bit number. If you've got an n-bit number and you say slide everything to the left by n, then you've just thrown everything away. You can't shift to the right with this operator. So the number of bits you want to move stuff around, you can't put a negative number there. But that's okay because we've got another operator for shifting things the other way. There's a right shift operator, and the one we're talking about here is called right logical shift. Well, on the previous slide, I skipped over that word in this operator, but This operator is usually called a left shift or a left logical shift. We'll make sense of logical in a moment because our next one's going to be right arithmetic shift. How does right logical shift work? Well, it's kind of like the one we just did. It takes all the bits and moves them to the right. Any bits that fall off to the right are just discarded. So here, if you started with CA and you said move everything to the right by 2 bits, well, the 2 bits that were on the right are going to get thrown away. All the remaining bits are going to get moved to the right by 2-bit positions, and 2 new high order zeros are going to show up on the left to fill in the vacated space. Same thing here, if you shift by too much, you could throw everything away. So the shifts that make sense would be between 0 and n-1 for an n-bit number. Oh, and I didn't say this before, this only works for integer types. So you can't shift bits around in a floating point number. You could still do that. You would just have to do some tricks with the type to make it work. It's not usually a useful operation for floating point numbers. I'm trying to think if I skipped over any other important details. Yeah, so this operand is always expected to be an integer for this number. All right, how about that other type of right shift, arithmetic shift? Arithmetic shift is kind of like what we saw with sign extension. It's for working with an operand that's signed. It's written the same way. It's written with the same operator, 2 greater than signs. It slides all of the bits to the right, discarding any ones that fall off the right-hand side. But for the left, it puts in not zeros, but copies of what used to be the high order bit. So I showed 2 examples to illustrate this. In this top case, if this was a byte and that was its high order bit, then when you slide it to the right, you get copies of a 1 in these extra high order bits, because that's what used to be the high order bit. Same operation, but if you started with this number, you get copies of a 0 in the high order bit. And the reason for this behavior is it preserves the sign of the number. Remember we said for signed numbers, the high order bit tells you whether it's negative or positive. Well, if you started with a number like this, it would be negative. Sliding in copies of extra 1s on the left, that at least keeps it as a negative number. This one would have been positive because it's high order, would have been non-negative. It would have been 0 or positive. So it's high order 0. When it slides to the right, if I put in additional high order zeros, then the result is still positive. The thing I forgot to mention a moment ago that I'll go ahead and say is these operators don't change their operand. Just like, adding or multiplying, those don't change the values that you're adding or multiplying, they compute new values. And that's what this does. This operator evaluates to a new number that's x shifted to the right by some number of bits. Backing up a couple of slides, this operation gives you a new value. It evaluates to a result that looks like x shifted to the left by some number of bits. So we talked about left logical shift. We talked about the 2 flavors of right shift, logical and arithmetic. And remember, it's the sign of the left-hand operand. It's the signedness of the left-hand operand that decides which one you get. If x is a signed value, then this operator will do right arithmetic shift. If it's not, if it's an unsigned number, you'll always get right logical shift. I mentioned Java has operators like all of these, but remember Java doesn't have unsigned values. If you make an int in Java, it's always going to be a signed int. So how do they handle this? Java did this with just 2 different operators. If you looked at the operators in Java, you'll see one is written like this, greater than, and it's got another operator that's written as 3 greater thans. And that's so that it can support write arithmetic shift using one of the operators and write logical shift using the other one. Questions before I try and move on?
Yeah, so the left shift, does it discard anything or does it just keep everything the way it is?
Oh, it definitely discards. Like here, if you computed this result, so this is 8 bits, so that's a byte. If you slide it to the left by 5 bits, and then you put the result in a byte, it's not going to have room to hold the stuff that slides off to the left. So my picture doesn't show this, because in my picture, I'm being kind of vague about where you're going to store the result. But if you slide it to the left by 5 and put it back in a byte, then that bit, that one, that one, that one, and that one are going to fall off the end. And you're only going to end up with a result that has these 3 bits, but they're going to be moved to the left by 5-bit positions. Here I'm describing it as if it's when you store the result that you lose those bits, and that could happen. Or if you just started with, like if you started with a long value, a 64-bit value, and you slid stuff to the left, then it's going to be lost as soon as it slides off the left end of that long. I just couldn't fit that on my slide because I don't have room to draw 64 bits. Hopefully that made sense. Other questions? All right. One trick you'll see with these operators is at least when you're working with unsigned values, sliding bits to the left or the right is a cheap way to multiply them, as long as you just want to multiply them by 2 or any power of 2. I probably said that a little bit wrong. Let me try to say it better. Sliding bits to the left is like multiplying them by 2 or 4 or 8 or 16, any power of 2 you want. And that makes sense because that's how binary numbers are represented. If you take a bit and move it to the left, then it's worth twice as much. If you move it to the left by 2 bit positions, that bit is worth 4 times as much. Sliding bits to the right is like dividing them by a power of 2 and truncating. So you can use this as a cheap way of doing multiply and divide operations, as long as you only want to multiply and divide by a power of 2. But in computing applications, multiplying and dividing by a power of 2 is pretty common. So that's a kind of thing that it's handy to be able to do. And you could use this to build fancier operations like building a multiply by an arbitrary amount based on shifting and adding. And internally, some hardware does things like multiply by doing shifting and adding. How else could we use these operations? Well, I made up some typical things you might want to do. So we've learned all the building blocks. Here's the 6 new operators, and here's what they each do. But what kinds of things might you want to do with them? Well, I listed here. Maybe you want to pick an individual bit and change it. We'll usually say clearing a bit is making it into 0. Setting a bit, we usually say that when we mean make it a 1. So maybe we'll want to set or clear 1 or more bits that we get to choose. Maybe we'll want to check 1 or more bits. We'd usually say you want to test a bit or test multiple bits. We'll figure out how to do that. Maybe we just want to print out a number in binary. If we can look at individual bits, it ought to be easy to do that. Maybe we want to copy sections of bits around. Like we want to go get 4 bits out of one number and copy it into some other number. And at the end, we'll figure out how to implement our own bit fields using these operations. All right, let's go through trying to do these. First, a couple of tricks that you can think of as a handy way of clearing selected bits. Not just 1 bit, but as many bits as you want all at once. And you kind of already know how to do this. That's one way of thinking about what the AND operator does. Same old AND operator we talked about before. This is just a common way of how it's used. It can do a pretty good job of clearing any bits you want as long as you prepare what's called a mask. A mask is just a number in binary that says which bits you want to clear. Again, we're not changing what the AND operator does. This is just a different way of thinking about what it does. With the AND operator, if you've got some number that you want to clear bits in, we'll pretend the top number is some number you've read from the user or from a file, and you want to clear the red bits. So you want to leave this top 0 unchanged, you want to leave this 1 unchanged, but you want to change these next 2 red bits to 0. You want to leave this next bit 1, you want to change this next bit to 0, you want to leave this next bit unchanged, and the low order bit, you want to make that a 0 no matter what. And we'll do this if you make, again, we call this a mask. If you make a number, if you make a mask, if you build a value that has 1s for all the bits you want to leave unchanged and has 0s for all the bits you want to clear. If you have a mask like that and you AND it with the number you started with, it'll do exactly that. This 0 is here because there was a 0 in the mask. This 0 is here because there was a 0. At least that's one explanation for it. The 0 is here because there was a 0 in the mask. Didn't matter what the other bit was. If there's a 0 in that position in the mask, the result's got to be 0, whether or not this top bit was a 1 or a 0. Same argument for the 1s in the mask. If you have a 1 here, then this output bit is going to be determined by the input one. The output bit's going to be a 0 if the top one is a 0. It's going to be a 1 if the top one's a 1. So you can think of this as letting bits pass through wherever there's a 1 and get cleared wherever there's a 0. So the bitwise AND operator is good for clearing selected bits. That's what I'm showing here. Let's pretend you had a number like D3 in hex. In binary, that would be 1101 0011. But let's say you didn't even know what the value was. Maybe you read it from some input source, but you wanted to clear the low order 4 bits. You just have to prepare a mask that has 1s for the bits you want to keep and 0s for the bits you want to throw away. And in hex, that would be F0. If you look at that in binary, the blue bits are the ones I want to keep. So I'll put a 1 there. The red bits are the ones I want to clear. So I put 0s there. And if you AND that with your value, it'll do exactly that. If you wanted a mask that cleared every other bit, all you have to do is prepare a mask with 0s wherever you want to clear and 1s wherever you want to keep a value. So AND operator is good for clearing selected bits. You just have to be able to make a mask that says which ones to clear. OR operator is good for setting selected bits. You just have to prepare a mask that says which ones to set. The way to prepare it is kind of like the AND operator. The rules are just different. You put a 0 wherever you don't want a bit to change. So that's kind of backward from how AND works, but you can see here the black bits are the ones I wanted to leave unchanged. So if you think of this second operand as the mask, and this first operand, that's the value I want to modify. Wherever I put a 0 in the mask, that's where I get a copy of the top number unchanged. So because there was a 0 in the mask here, the output bit is determined by whatever was above it. Because there was a 0 in the mask here, I just got a copy of what was above that 0, a copy of that bit from the other input value. But wherever I put a 1 in the mask, the output bit is going to definitely be on. So if I put a 1 here, doesn't matter what this input bit was, the output bit is it's definitely going to be a 1 there. Here, I put a 1 here, and it didn't matter whether the bit above it was 1 or not, the output bit is going to be 1. So OR is good for setting selected bits. It lets you pick bits you want to turn on. You just have to prepare a mask that says which bits you want turned on. You put a 1 there. Which bits you want to leave unchanged, you just put a 0 there. So similarly, if you had some input value and let's say you wanted to set the 4 low order bits, a mask like 0F would do a good job at that. Here's what it looks like in binary. I put 0s in the top 4 bits and 1s in the bottom 4 bits. So in the result, I get a copy of the first operand wherever I had a 0 in the mask. And I definitely get a 1 in the output wherever I had a 1 in the mask. It didn't matter what was in the first operand there. I definitely got a 1, or I will get a 1 where there's a 1 in the mask. Just another example, if you wanted to set the high order and the low order bit, you could make a mask that just had 1s there and 0s everywhere else. And if you OR with that mask, that's what you'll get in the output. I'm sneaking in one trick here. I don't know if we've seen this before, but these operators have assignment versions of them. So there's a infix OR operator that goes between its operands, or there's an OR equals, which ORs, in this case, X with this mask, and stores the result back in X. The nice thing about these versions of the operators is it's a little harder to make mistakes with the precedence here. It's easier to get that right. Just to complete the set, if AND is good for clearing selected bits and OR is good for setting selected bits, the other one, exclusive OR, is good for flipping selected bits. If you prepare a mask and you put a 1 for any bit you want to flip, and you put a 0 for any bit you want to leave unchanged, that's one way of thinking about what the exclusive OR does. Here, if you think of the red bits as the one I wanted to change, I put a 1 there, or the ones I wanted to change, I put a 1 there in the mask. The 0 or the black bits are the ones I want to leave unchanged. In the output, that's what I get. Here, I put a 1 in the mask, so this 0 got flipped to a 1. This 1 got flipped to a 0. For the next 2 bits, I put a 0 in the mask. So this 1 got copied through unchanged. This 0 got copied through unchanged. At the bottom there, I'm showing an example. You could use this to easily flip just 1 bit at a time, leaving the rest of them unchanged. Any bit you want by preparing the right mask, or flipping any number of bits that you want by putting 1s in the mask there. Questions? All right, so we said we want to be able to use these operators to kind of pick how we want to change particular bits. And we've seen it's not that bad to do that as long as you can make the right kind of mask. Same idea for testing bits. What if you want to look at a number and say, well, I want to know if this bit is on or not, or I want to know if this particular set of bits are on or not. This is really just an application of masking. With the AND operator, you can prepare a mask that throws away, and when I say throws away, I mean turns them into zeros, and any bits you don't care about. So let's say you wanted to look at just these red bits I've drawn in this example, just the bottom 4 bits in a number, the low order 4 bits. I made a mask that keeps those 4 bits and throws away all the others. So that would make it easy to look at just those 4 bits. So by ANDing some number with that mask, I'm left over with just those 4 bits. And when I say left over, I mean, well, everything else got switched to a 0. So that would make it easy to test those bits. But I guess there you might want to say, well, what kind of test do you want to do? Do you want to know if any of those 4 bits are on? Do you want to know if all of those 4 bits are on? You can have either. It just affects what you do after you've masked off all of the other bits. And that's what I'm showing down here at the bottom. Let's say you've got this number. I just made it up, 0, 1, 1, 0, 1, 1, 0, 0. And you want to know if any of the low order 4 bits are on. You can AND with a mask that just keeps those 4 low order bits. And then if the result is 0, well, none of them were on. If the result is non-zero, at least one of them must have been on. And that's what I'm testing right here. I take some number X, who knows where you got it. I AND it with a mask to throw away everything except the bottom 4. And then if it's non-zero, at least one of those bottom 4 bits must have been on. If you want to check them all, instead of comparing against 0, you just have to compare against the mask itself. If you take that number X and you throw away everything except the stuff that's in the mask, except the low order 4 bits, and it's still equal to the mask, then all 4 of those bits must have been on. So these 2 tricks give you an easy way to see if any bit in a set of bits is on, or if all bits in a set of bits are on. And you get to pick the set that you care about. Questions before we move on to the next trick? All right. A pretty reusable trick is something people call a movable mask. So far, we've been talking about a mask as if you figure out, which bits you care about. You write down a number, probably in hex, that has either zeros in the spots you care about or ones in the spots you care about. But what if you wanted to be able to compute a mask, one that could look at any bit? A movable mask is good for doing that. And that's really just a fancy name for a tiny little bit of code. And here's the tiny little piece of code. Here I've got the number 1. I wrote it in hexadecimal to make it clear that I'm thinking of this as a bit pattern. But it's really just a plain old 1. It's a 1 in the low order bit and zeros everywhere else. If I take that 1 and I slide it to the left, I can pick how far I want to slide it to the left using a variable. So if I slide it to the left by 0 bits, it's going to have a 1 in the lowest order bit. If I slide it to the left by 1 bit, it's going to have a 1 in the second lowest order bit. Normally bits are counted from 0 as the low order bit. So if I slid it to the left 2 bits, it's going to have a 1 in bit position 2. If I slid it to the left if I shifted it to the left by 17 bits, it would have a 1 in bit number 17 and a 0 everywhere else. So this is a movable mask. It's a way of letting you make a mask, compute a mask that has a 1 anywhere you want. And when I say anywhere you want, I mean you could have a variable that decides that. You could loop over all the bits. And zeros everywhere else. Sometimes it's handy to have a mask, and sometimes it's handy to have the opposite mask, usually called the complementary mask. And this is where the tilde operator comes in handy. If this is good at making a mask that has a 1 anywhere you want and zeros everywhere else, if you put a tilde in front of that, it gives you the complementary mask. So this is an easy way to make a mask that has a 0 in just one place and 1s everywhere else. Here, precedence is worth thinking about, because if you did this instead, if you left out these parentheses, remember tilde has really high precedence. So this, if you just wrote it like this, it would flip all the bits in this number and then slide them to the left, which wouldn't do exactly the same thing, because when you slide them to the left, it's going to introduce new low order zeros. Whereas if you do it like this, it's going to slide this 1 to the left by this many bit positions and then complement that result. So it won't introduce a lot of extra low order zeros computing it this way. What's this useful for? Well, I made up an application. Let's say you just wanted to count the number of 1 bits in a number. I made up a number up there. I called it secret, and I just typed in some digits. I wonder how many 1 bits are in the representation of that number. A movable mask would let us compute that. I wrote a loop here that iterated over all the bits. I didn't even say, well, that's a 32-bit number, but I let the compiler help me decide that. However many bytes are in an int, it has 8 times that many bits. So I just loop from, in this case, 0 to 31. And then I look at each of those bits, bit number 0, bit number 1. I do that by using my movable mask to slide a 1 bit I positions to the left. I AND that with my number, so that'll throw away everything else and just keep that 1 bit. And if the result is non-zero, I count it. It must have been a 1 bit. In fact, I even use this as a truth value. Anything that's 0 would be false. Anything that's non-zero would be true. And then at the end, I report how many 1s were in that number. You could do this to do a lot of different things where you wanted to look at individual bits in a value one at a time. There are a couple more tricks that we ought to be able to do. And one of them we kind of already mentioned. What if we want to go get some bits out of a number and we want to move them somewhere else? We just want to copy not the whole number, but just selected bits in it. This is easy to do using really nothing more than masking. So let's pretend you've got a source. I'm writing it down as if it's a byte just to make it fit on my slide, but if it's a byte, it's 8 bits. So pretend that's your source. You want to go get not all of the bits in that number, just the middle 4, the ones I colored red. And you want to copy that into the destination. Same location. You want to replace the middle 4 bits with a copy of what you got from the source, but you want to leave the other bits unchanged. So it's kind of like you want to go get part of what's in a byte and copy it into another byte. This is easy to do with masking. Over on the left, I think of this as, well, let's go get just the middle 4 bits out of the source. I made a mask. I ANDed with that mask, and I put 1s for the bits I wanted to keep. 0s elsewhere throws away the other bits. I get 0s for those. But for the middle 4, I get a copy of whatever came out of the source. In the destination, let's make room for the bits we want to copy over. And when I say make room for them, let's clear out anything that used to be in those bits. That's another good job for AND. I can make the complementary mask, where I keep everything except the 4 middle bits, but the middle 4, I turn those into 0s by putting 0s there in the mask. So now in the source, I've got, at least from the source, I've just got what was in just the middle 4 bits. In the destination, I've cleared the middle 4 bits. So if I OR those two things together, I should get a combination of them. This bit is a 1 because it came from the destination. This next bit is a 1 because it was one of those middle 4 bits from the source I wanted to copy. And I won't read through all of these, but in general, these middle 4 look like what I got from the source. The other 4, the first 2, the high order 2 and the low order 2, those got here because they were copied from the destination. So this trick would let us go get any section of bits from any number and copy them elsewhere. We could use tricks like this to implement what people would usually call a bit field. A bit field would let us take a big number like a 32-bit int and carve it up into little regions that we could use to store different things. And this is what I mentioned near the start of lecture. What if you had something that was so big or that you wanted to compress so well that you wanted to store things just in part of an integer, not wasting the whole integer. Maybe you want to take this 32-bit int and you want to use 7 of its bits to store one number. You want to use 9 bits to store something else, 2 bits to store something else, 14 bits to store something else. Using tricks like the one we just talked about, we ought to be able to do this, and we'll call this an implementation of a bit field. We'll use an example like the one we just talked through to illustrate this. Let's say we wanted to use the middle 4 bits in a number, in a byte, and we wanted to store a number there. But we wanted to be able to go get that number, do math on it, put the result back where it came from without affecting any of the other bits. And if we're backing up a slide, if we want to do this, we want to be able to do things like change what's in these 9 bits. Maybe we want to add something to that without messing up what's in the surrounding parts of that number. So let's pretend we want to go get what's in these middle 4 bits and maybe do some math on it. Well, we already know part of this. We can use a mask to get just those middle 4 bits. And when I say that, I mean we can mask off anything we don't care about. We can use the mask to turn all the other bits to 0, so we're left just with what was in the middle 4 bits. If we're going to do math on this, the fact that these bits are in the middle of a value is going to be problematic. If we were going to do math with this and that's the low order bit of what we got, we'd really like that to be over here in the low order bit position. Otherwise, it's going to be hard to do math in a way that makes sense. So the shift operator could fix that for us. If we take these bits and move them to the right by 2-bit positions, well, now the low order bit from these middle 4 got moved into the actual low order bit position, and everything else got moved to the right along with it. So now we're ready to do some math with this. Let's say we wanted to do some math with it and put it right back where it came from. So it's like we want to go get the middle 4 bits. We want to be able to compute with what's in just those bits and then store the result back in a 32-bit number. Let's say we wanted to add 1 to it. Well, once we've got a copy of the middle 4 bits and they're shifted to the right so that the lowest order one is in the 1's position, we ought to be able to just add to that or do any other math we want to, just like any other number. But then we have to do a little bit of work to put the result back where it came from. And that's most of what this slide shows. This is our result. So if we started with 1011 and we added 1 to it in binary, the result would be 1100. If we want to put that back in the middle 4 bits of the value they came from, well, we better slide those bits to the left. The shift operator is good for doing that. It's possible that when we did this addition, maybe we got an overflow. Maybe, especially if we'd done something like multiplication, we could easily overflow out of those 4 bits. So we don't actually need it in this example, but in general, before we go store this result in the byte that it came from, we better mask off any other bits so they don't affect surrounding bits. So I use AND for that. I AND with a mask that just keeps the middle 4 and throws away the 2 high order and the 2 low order bits. Again, it doesn't really change anything here, but for a general operation where overflow could have happened, it seems like this is important. All right, so now I have the result and the surrounding bits are guaranteed to be 0 because I just did this masking. Let's go put those 4 bits of result back where they came from. I take my original source, and if you back up a slide, I'm pretending that's the byte you started with. I want to replace just the middle part with the result of my calculation, adding 1. So I'll clear the middle 4 bits by ANDing with the complementary mask here. And then an OR, a bitwise OR, will put the 4 bits from my result in the middle 4, and the remaining bits, the outer 2 on each side, will be unchanged. This is kind of a simple example, but backing up a couple of slides, we could have used this same trick to do as complicated an example as you wanted. We could take any primitive type and we could break it up into fields of any number of bits. And then using tricks like this, we could manipulate any of those bits, parts of the bit field individually. Questions before I tell you why it's good to be able to do that, but it's also good to get some help from the compiler on that. All right, sorry, I gave a bad introduction to this, but what I should have said is something more like, yeah, that's good to be able to do. And I'll tell you some in a moment of why it's good to be able to do that. But the compiler can already help you with some of that stuff. You just have to know how to ask it to do that. The compiler can implement bit fields itself, not everywhere, just in the fields of a struct. When you define a struct, well, you define it like this picture on the left. You put in as many fields as you want, and the fields are all based on primitive types. So I'm pretending I'm storing a color with red, green, and blue components. Alpha is sometimes used as a transparency value in color, so I'm pretending I've got that. I made red and green 16-bit values, and I made blue and alpha 8-bit values by storing them in unsigned char. That's really just to make a more interesting example, but you might have situations where maybe you're more sensitive to red and green, so we want more precision on those. And maybe we don't need as much precision on blue and alpha. So there could be some applications where this made some sense. If you made a struct like this, and then you ask the compiler how much memory it takes, it would say 6 bytes. The memory for this would be laid out like the picture I'm showing here. Red would take 2 bytes as a short, so would green, and blue and alpha would take each a byte apiece. So 6 bytes for this. But what if 16 bits for the red component was way more than you needed? I mean, in reality, you can't perceive that many different levels of red intensity. Maybe 9 bits is plenty to store the range for that. Maybe 9 bits is plenty for green, and maybe blue and alpha only need 6 bits. Bit fields let you do this in a struct, and I'm secretly showing the notation for that here. If you have an integer type, then the name of a field, and then colon, and some compile time constant. That constant specifies the number of bits to use for that int. So here I'm saying, well, red is an int, but only use 9 bits to store it. Green, only use 9 bits for that. Blue, only use 6 bits for that. The compiler will lay out the storage of these so that, well, if red needs 9 bits, it's going to need all 8 bits from one byte, and then 1 more bit in the next byte. Green, well, there's 7 bits left over in the next byte, so it can have all 7 of those, but then it's still going to need 2 more bits in the remaining byte. It'll actually store your fields so they may not fall at byte boundaries in your struct. Doing that's going to take more work to access those fields, but it could save on memory. And if you ask the compiler, how many bytes does it take to store this representation of color, it'll be able to pack that into just 4 bytes by doing the trick I'm trying to show in my picture. The nice thing is, once you've asked for this, you can use it just like any other struct. So here I'm using this struct that has bit numbers specified, packed color, I called it. Here I make a variable of packed color type. You can initialize it just like any other struct. You can go get its fields just like they were plain old ints. When you do this, the compiler is writing masking and shifting code like the code we just figured out how to do. It's just we don't have to write it ourselves. You can individually assign stuff to these fields, even though they're not stored. This blue is not stored in just 1 byte. It's spread across multiple bytes. You can even overflow them individually, and they don't affect their neighbors. Here, if red is 9 bits, then 511 is the biggest value it can store. That would be the largest thing a 9-bit int could store. If you add 1 to it, it's going to overflow, and it can. It would wrap back around to 0, but that overflow wouldn't affect any of these other fields because the compiler's writing code backing up, just like what we did here. As it does these operations, it's masking off the result to make sure changes to one field don't affect other fields. You do lose one thing when you do this, and that is you can't take the address of a field in a struct like this. That's maybe a little thing, but it makes sense if you've carved up the representation of a struct into individual ranges of bits. Well, only bytes have addresses. The individual bits in your computer, those don't have addresses. So if you said store this using just some bits, you can't then ask about the address where that starts. You could ask about the address for the whole struct, but not just one of its fields anymore. Questions before my next slide? Right. Yeah.
Does this like affect the padding alignment when you do this? Like, will your struct have that padding anymore or not?
It could still have the padding. And I'm about to say this in a slide. Exactly what the compiler does when you say this, it's kind of up to the compiler. You're saying, oh, this guy only needs 9 bits. And since I bothered to tell you, please try to store it in just 9 bits. But the compiler could still introduce some padding. In this one, sorry, I was counting bits there. I've only asked for 30 bits total. So like my picture shows, there's actually going to be at least a couple of unused bits at the end. That's not really padding. It's just, well, an instance of a struct has to start at a byte boundary at least. So it will pad there. It might do some padding elsewhere. I don't know if there's a good way to check that on the common platform, but I did check this and I did get 4 bytes for this. So it is kind of spanning fields across byte boundaries in this case. But I would say the compiler is still permitted to do some padding there if it wants to. Other questions? All right, here's what I was stalling for, because at this point you might feel like I wasted your time. We spent maybe 10 minutes figuring out how to implement bit fields ourselves. And then I said, you don't have to do this. The compiler knows how to make bit fields. So you might think, oh, so I'll never have to do bit fields myself. And well, it'd certainly be good to take advantage of what the compiler could do for you. But the problem is bit fields implemented by the compiler are not portable. And that's kind of what we were just talking about. The way a compiler takes a struct and carves it up into regions of memory is specific to that compiler. If you wanted to write portable code where you got a byte and you just needed to look at a couple of bits in it, then you're going to have to write that code yourself if you want to write it in a portable way. Bit fields in a struct are still useful, but only in some applications. If you had a program and you just wanted to reduce the amount of memory it took while it was running, bit fields could let you do that and you might not have to worry about portability. If you were never going to save results from that program in a way that had to be read by a different program, or I guess said better, if you were never going to save the contents of a struct that used bit fields and then read it from a different program, then portability probably doesn't matter to you. If you are just trying to pack stuff into limited memory, you may not have to worry about portability. But if you have to read a data format, like a packet on the network, and you have to look at individual bits, you're going to have to write your own code to do that if you want that code to be portable. So it's handy to have both of these. If you can get the compiler to do bit fields for you, that's probably worth doing. If you can't, if portability is necessary, then it's good to be able to write that code yourself. And that is all I've got to say about bitwise operators. We're done about 5 minutes early, so I'll invite questions if you have them, and I'll still hang around a couple of minutes after class if people have questions. I'm still recording in case anyone wants a question recorded. You'll have an exercise where you get to work with the bitwise operators, and we'll feature that on project 5. So one of the things you'll get to do is access the contents of a file and create the contents of a file by working with individual bits, not individual characters or even individual bytes. You'll be accessing sometimes just one bit at a time. So you will get a chance to use what we talked about today. One more thing, and then I'll stop recording. And a lot of the stuff that I showed you today, even though you probably never did use it in Java, it's there in the Java language. So it has support for these same operators, plus that extra right shift operator that we talked about. All right, let me go ahead and stop recording.